Okay, so hi everyone. I'm Alysa Obertas, as Eric mentioned. I'm a student at University of British Columbia. Currently, I'm on co-op at Triumph. I'm working with the theory group under Peter Nabertian. So my project is working with alpha-alpha scattering. As it's a current project, as I'm sure many of you know, things don't always go as planned, so I was hoping to have it done. My program works, but for some constants, so I couldn't get my results up. But I'm still going to go over what I'm working on, and I think it's really interesting, so I thought I'd share it with everyone here. So when we think about scattering, you have your nuclei. One of them's going towards the other. You have your target nuclei sitting there, your projectile one goes off, it bounces off, it scatters. Okay, well, in this case, particles, not exactly, hard spheres that are actually just going to bounce off each other. So we have to think of things a little bit differently in the realm of quantum mechanics, of course. So with scattering, typically there are two types of scattering. You're going to have elastic or inelastic. With elastic scattering, you can think like classical physics, just your transfers of energy. Inelastic, you can get excited states with your nuclei. You can also have new particles that are coming out after they've scattered. So something we're going to consider, instead of just having them be their solid objects that are bouncing off each other, there's going to be a scattering from a potential. So the potential that we're going to be looking at here is the sum of the nuclear potential and the Coulomb one. So the nuclear force here is attractive short range. The Coulomb force is repulsive in long range. We're only considering the protons here. We don't really pay attention much to the electrons. So this is repulsive and it's long range here. So to simplify this further, we're looking at a spherical potential. And the result of this is that we're only going to have elastic scattering. Anyhow, it's easier to look at, so it's a little better in my case. Another thing that makes this much easier to work with is to solve it in the center of mass frame. So essentially, you end up with an effective particle. And now, experimentally, this isn't going to be the case. In your frame, you have your target nuclei that's at rest and your projectile one going at it. But once you've solved in the center of mass frame, you can just do some transformations, and it's done like that. So here now we have this potential that our effective particle is essentially scattering off, and it scatters at some angle theta. We don't really know what that is. Another way that we can look at this is far away, looking way outside of the nuclear range. We can consider the incoming one as a plane wave, and then the scattered wave we can think of as a spherical one, and it has some scattering amplitude that is dependent upon which angle it scatters off of. So something that can happen during this scattering is that the wave function can accumulate a phase shift. This ends up being quite important. It's very relevant. Another thing to consider is what this scattering amplitude actually means. So it's related to the probability that it's going to scatter off at that angle. And this is also tied in with the cross-section of the reaction, which is effectively the probability that this reaction is going to occur at that angle. And it's measured in actual physical area units, but effectively it's just the probability. Now, the cross-section, as I'm sure if you've were at any of the talks for nuclear physics or any other things where you have particles hitting each other, cross-section is very important both in theory and experimental physics. So finding out what this cross-section is quite important. So our scattering amplitude is related to just this angular cross-section by this relation. So what do we need to do? We need to find the scattering amplitude. And to do this, we can just solve Schrodinger's equation. Okay, well, that's a little easier said than done. So how we can break this up, we can consider separation of variables, our greatest tool when we have a difficult problem. And we can break it up just through partial wave expansion. That just means looking at the individual orbital angular momenta. So what's important here is that we have this radial term, UL of R. And this is now what we need to figure out. So what we do is we're going to match these two up outside of this nuclear range, as I mentioned, which is where this asymptotic form down below, actually, you can apply it. Okay, so now when we match it up, we can find out what this scattering amplitude is, but of course to do this we need to find out what this radial component actually is. So if we actually take that partial wave decomposition and put it into Schrodinger's equation, we're going to get this partial wave equation. It's probably very familiar for those of you who've done quantum mechanics. This just looks like when you're working with your hydrogen atom. So what we end up doing when we're solving it, I'm not going to go through the details, otherwise there'd be a lot of steps in between. But it ends up depending on a parameter that's called the S matrix, and then our zero potential solutions, which we call IL and OL. Essentially, asymptotically, they resemble incoming and outgoing waves. So that's why they're represented like that quite frequently in the literature. So another note about these is I've called them zero potential solutions. So these are just the solutions outside of the nuclear range. If there are Coulomb forces, these Coulomb forces will be incorporated into those. If there is no Coulomb force, i.e. you just have something that just has neutrons, you're not going to have this Coulomb force anywhere between your nuclei, then those are zero potential solutions. So now this S matrix, we need to figure out what that is. This is very related to phase shift, quite directly just through an exponential relation. So once you find out what your phase shift is and what the S matrix is, you can figure out what your radial component is and get your complex amplitude. Okay, so these zero potential solutions are well known. We don't have to worry about that. We do have to worry about our S matrix. So one way to represent it is through this R matrix, so many little components, but this R matrix is now what our new goal is. And this is actually what I'm working on with my code. So effectively what I'm doing with it, there are a few different ways to get it. I'm using something called a shifted Legendre mesh. Basically you have a whole bunch of mesh points. You sort of evaluate it with what you make up as a basis. This is where the Legendre part comes in. You treat your basis points as functions that are just from a shifted Legendre polynomial. And then you sort of solve it, sum up your matrix points, and then you end up getting what this R matrix is. So once you have your R matrix in, you can figure out what the phase shift is quite easily, and then from there on you get all of your other things. So moving on, just looking at this phase shift, it is very important to figure out what the phase shift is in order to obtain your radial component of the wave function, as well as the scattering amplitude and then the cross-section. But another parameter that it has, or usefulness that it has, is that you can look at the resonance of scattering. So when you think of the particles going towards each other, they're going to have this attraction, obviously, as they get closer because of this nuclear force. But ultimately, because they do have positive energies, they're going to go together, sort of maybe stay there for a while because they're attracted to each other, but then move apart. And if you want to look at what's sort of happening in the middle there, you can look at this resonance. So it effectively is sort of resembling what happens if it were a bound state there. And the width of this resonance is reflective of how the time it spends sort of acting like that bound state. And the width is where it goes through a 180-degree phase shift change. And the resonant energy is just sort of at the midpoint where you have it at a 90-degree change. I believe numbers might be slightly off, but effectively it's just where it goes through a significant phase change to consider that this resonance happens. So as I mentioned, we look at it only for individual orbital angular momenta. So for any individual L, we just look at the phase shift, and this is just dependent on the energy that you put into your system. So for different energies, you can plot what the phase shift is and figure out what this shape looks like to figure out what your resonance is, your resonant energy, and the width is. I should note just sometimes the system won't have a resonance, and sometimes it also can be difficult, even if it does have a resonance, to determine exactly what the width is or what the resonant energy is. So talk about that in just a second. But looking back at this R matrix that I'm finding, I know I haven't shown a whole lot of information about it, but essentially it's just a computational technique, and it can be quite useful. So my situation I'm going to be looking at is alpha-alpha scattering, and what I'm doing is I'm taking the alpha particles, considering them point particles. They have a simple potential between them. It's usually modeled as a Gaussian or something called a Wood-Saxon. But basically, this is a very simple situation. It's been looked at before. It's not going to provide a lot of new information to the field of theoretical nuclear physics, which is fine. The main importance of what I'm doing at Triumph is the code that I'm writing. So this R matrix solver can be quite useful for other things, for more complex, a little more realistic situations. So something you can do is you can expand upon it to allow for inelastic scattering. And these are called multi-channel reactions. You can also put in solve for bound state energies, which obviously is going to be useful when you're looking at bound states instead. You can also factor in, now instead of having point particles, obviously we know our nuclei are composed of protons and neutrons. These do have structure, and we do want to have potentials that factor this in. So you can add that to your R matrix code as well, so you get more accurate results. Another thing that these R matrix codes are capable of doing are looking at capture reactions. We might take in a proton or a neutron. And as I mentioned before, sometimes if you can't actually figure out really well what the resonance is like, you can actually put in complex energies to examine it further. And even though this isn't a realistic situation, you're not going to have complex energy. Energy is very real. You can learn more information about it. And this part here is actually going to be my main contribution to this R matrix code that I'm doing for Triumph. I'm hoping that it'll be a very useful thing for the theory department that'll get used. So, thank you. Questions?
Thank you very much. Any questions?
Okay. Yes?
So, you said that the potential between nucleons has been studied extensively.
Well,
What stacks it? You mentioned some other things.
yeah, so effectively what those potentials are, they're modeled from experimental physics. So it's just if you pretend that you have point particles, you sort of go through and say what potential would give these results. You can find the phase shifts, your experimental data, and then you sort of reverse engineer a potential, and then you can use that potential to further study it. That's my understanding of how it's obtained. So it's a fairly, I believe it's, what I'm doing has been studied for a while, probably since like say the 50s. It's very sort of straightforward in terms of really light nuclei that are quite tightly bound. It's not too drastic to consider it them point particles. Is that what you were asking? Sort of?
Well, I was wondering which one you're using.
Okay.
Are you using experimental results for that?
For the potential?
Yeah.
Well, there are some parameters that have been fit to experimental data, so those can be used, but I can also play around with them as well to see what sort of will then fit experimental data too.
Another couple of minutes for questions. Is there one more?
But yeah, both can be used to see which sort of works better. My understanding is just playing around and seeing what looks nice.
Okay. Thank you very much.